Hello and welcome to the third video of this series. In this video I want to talk about the GROOPS parser and how it can make your life easier and how it can make your group scripts more flexible. So I've prepared a short script. I'll talk about it in a second, but the purpose of the script is to compare kinematic orbits to dynamic orbits of a satellite and visualize this in a plot. So the result should look something like this. So we have a long, cross, and radial axis, the kinematic orbits, which are noisy compared to a dynamic orbit, which is relatively smooth. For this, we have some data. We have kinematic orbits and reduced dynamic orbits for 4 different satellites, GRACE 1, GRACE 2, Sentinel, and Parser, each for 1 week. Both kinematic and reduced dynamic orbits. And yeah, so if we start with our script, I'll go quickly through it. It's very simple. We do not have any global variables so far. First of all, we remove a temp directory in case it already exists. Next step is to recreate this temp directory fresh and also create the plot directory. And then the first real step in the program is to synchronize our kinematic orbit and our dynamic orbit. So we ensure that both contain the same epochs, which is necessary because the kinematic orbit might contain some gaps while the reduced dynamic orbit does not contain gaps. And as you can see here, here I've selected GRACE 1 for the 1st of January 2015, and the same here I've selected the reduced dynamic orbit. And both orbits are then written to their respective files, which only contain synchronized epochs, so epochs that are part in both files. Next step is instrument multiply add, where the 2 temporary files we just wrote are the dynamic orbit is subtracted from the kinematic orbit, and the result is written to orbit diff.txt. Finally, we want to visualize the orbit in a local orbit system, so we simulate a star camera 5 based on a dynamic orbit, and we rotate the differences from the celestial reference frame to the local orbit reference frame. And finally, we plot the result. We have 3 layers, 1 for each component, so long, cross, and radial. As you can see, we read the orbit file here, and value x is data 0, which is the modified Julian date, and the value data 1 is the first value, which is the long track value. We multiplied times 100 to convert it to centimeters, and add 5 centimeters to shift it in the plot. Yeah, that's basically it. We also set as the x-axis, we use a time axis where we can define the tick spacing and so on. So at the end, we end up with this plot where we have a long shifted by +5, radial shifted by -5, and yeah, values in centimeters and a plot axis. So far so good. As you could see, I just used here the orbits from GRACE 1. So now what if we wanted to do to visualize the orbit for GRACE 2? We could of course change it here to 2 and also here to 2 and run the script, and it would work fine. But that's already a bit inconvenient. So what we can do in GROOPS is we can create a global variable. Let's call it satellite. We will give it the type string and just call it GRACE 2. And instead of having GRACE 2 here, we can now replace this with the variable satellite. Same here. And now, when I run the script, satellite will be replaced by GRACE 2. Another location where we can put it is, for example, in the title. We can say, okay, we can have the name of the satellite in the title and also maybe in the file name. So let's say the file name should contain satellite, should be satellite_orbit diff. And if we now run this, goes by pretty quickly. And now we have a file not only called orbidiff, but grace2 orbidiff, and also it contains grace2 in there. And as you can see, it's different to grace1. The original one was grace1, so it's already pretty convenient. As I mentioned in the beginning, we also had data for 1 week, but here it's basically hard-coded to use the 1st of January 2015. We can also circumvent this by creating a global variable. Let's call it time, and it's from type time, and we can just say, okay, we want to visualize the 2015 January 2nd, let's say. As you can see, the modified Julian date value is this, and I can now replace the date here by variable time. But you have to be careful here. If I just use time, it would use 57024 as the value, because that's the value which represents the time. But of course, the file name does not contain the modified Julian date, but it contains the actual date. So here we can use another feature of our parser. We can specify a format. We could do year date, or as an alternative, we can just use percent capital D for date, so which will parse the date in the ISO format as shown here. We can do the same here. We can replace it, and again, this will be when I run the script, this will be replaced. What we can also do is add the date to the file name, and if I now run this, I should have another plot. Exactly, I have now this plot, which is called grace2 orbidiff _ 2015-0102 PNG. And as you can see again, this is different than the 1st of January we plotted before. And now it's easy for me to just plot, for example, X instead of grace2 and plot the 7th of January. So if I run this now, done, and then now I have a figure or plot Parser X orbidiff for this day in this satellite. So yeah, that's pretty handy. Another thing I want to show you is let's add another layer, and we'll use the same input file orbidiff, but instead of what we now want to do is we want to highlight outliers in our time series. So we can, let's define an outlier by the total difference being larger than 5 centimeters. So I can first compute the total difference, which would be data 1 squared plus data 2 squared plus data 3 squared. And let's say this should be, or rather, let's now add a condition. So we can write if this distance is larger, let's multiply it by 100. So let's do it in centimeters. If this is larger than 5 centimeters, then at value 11, value y of 10, or then use a value y of 10, otherwise use not a number. And what we want to happen is we want to have a symbol. Let's pick a diamond, black diamond, at the value of 10 on the y-axis if the total distance between the kinematic and the reduced dynamic orbit is larger than 5 centimeters. Otherwise, we use the value none, which is this function. So what you can see here is the parser can interpret mathematical expressions. There are quite a few of them. from square roots to normal mathematical operations, comparisons, and also specific functions. We can take a look at the GROOPS documentation. If you go to Parser, here's a list of the mathematical expressions that are supported, logical expressions, functions with multiple arguments, and so on. And there's also the text parser. You can see earlier we used percent year, month, day, but also %d, capital D, for the date. So here there's an explanation of these parser options you have. Okay, and if we now run it again, we should hopefully end up with see. So now in our Parser X figure, we have black diamonds at the locations where the total difference between the kinematic orbit and the reduced dynamic orbit is larger than 5 centimeters. So of course there are many more options you can use, or many more functions you can use with the GROOPS parser, but in principle it's super handy to simplify the script, make it more flexible, use the same script for different satellites, for different dates, and so on. And in the next video, we will use this because we will then extend our script to include loops and conditions. And there again, these expressions and the parser will be very convenient. So until the next video, see you. Bye-bye.